Okay, let's get started. This video is going to talk about relative atomic masses and how a mass scale was created to make discussions about atomic mass just be a little bit easier instead of referring to actual masses in grams because they're so small. So this video is going to talk about the relative scale designed to measure atomic masses, also how the periodic table number of atomic mass is actually an average mass of all of the isotopes of the element, and I'm going to teach you how to calculate the average atomic mass of the element. So we're going to go through a couple practice problems to prepare you to do more practice in class. So, as I was saying, the masses of atoms in grams is extremely small. So it's more convenient to use relative atomic masses. So they actually had to design a scale, and they set it up, just like we set up the Celsius scale, just to work well for us. So they set up a scale, and they had to choose one atom, and they decided to choose the carbon-12 isotope. So the key word here is arbitrarily. I'm sure they had rhyme and reason, but they could have picked any element. So the standard used to determine the relative atomic mass is the carbon-12 isotope. By definition, one atomic mass unit, AMU, equals 1/12 the mass of a carbon-12 atom. Now on the next slide, we see a list of common elements and examples of their isotopes and what their relative abundances are. So if you look at carbon-12, carbon-12 by definition has an atomic mass of 12. And they've taken every other element and compared the sizes of the atoms of each of those elements and have determined that carbon-13 has a mass of 13.003355. These spaces in this image are just used to be able to count the numbers quickly. It's just for reference of being able to see which numbers are there more easily. Now, if I take the mass of carbon, 12 and 13 and 14, and I add them up and I divide them by 3, I'm not going to get anywhere near 12.011. It's going to be close to 13. So when we look at the average atomic mass, it is actually a weighted average. It's taking into consideration that 98.90% of carbon is actually carbon-12. So if I had a room full of 12, let me start that over. If I had a room full of 100 carbon atoms, about 99 of them would be carbon-12. A little over 1 would be carbon-13, and maybe a trace would be carbon-14. Now I know this is very unrealistic because if I had 100 carbon atoms in there, these numbers don't really work out so well. But if I had 1,000, I could probably do it easier. But I'm hoping you get my point. So if you were to take the mass of all 100 of those and then divide by 100, you'd get something like this, 12.0111. So the periodic table gives a number, and that number is the average atomic mass of all of the isotopes. You can see the most common isotope is 16, oxygen 16. 99.762% of all oxygen atoms are oxygen 16, with just small amounts being 17 and 18. So when you look at the average atomic mass, it's not too surprising that the mass is 15.9994. When you look at the average atomic mass, oftentimes you can round this to the nearest whole number, and it will be most of the time what is the most abundant isotope. For example, hydrogen-1 is the most abundant isotope. If I take the average atomic mass and round it to the nearest whole number, we're rounding it to 1. Carbon-12 is the most abundant. This would round to 12. Oxygen-16 is the most abundant. This would round to 16. Copper-63 is the most abundant. And you see that this rounds to 64. So here's one situation where it doesn't work out so well. There actually isn't a copper-64. But we do the best we can. If I give you any problems, I will give you the actual isotopes that exist. Otherwise, we just work through it as best we can and make some assumptions if we have to, and sometimes those assumptions might be right and sometimes they might not. So let's continue. When you look at the mass of our subatomic particles in atomic mass units, you see that an electron is very, very small. Just like in our previous discussion on isotopes, when I gave numbers in grams, it was something times 10 to the negative 28th. Protons and neutrons are about the same size, and they're close to 1. So for all intensive purposes, you don't need to memorize these numbers. Let's say that a proton has a mass of 1, a neutron has a mass of 1, so they're approximately the same mass, just like positive Patty proton and nerdy Nelda neutron are in the nucleus arcade. And an electron's mass is negligible. We say that it has a mass of 0, even though we know it can't technically have a mass of 0. So, for convention, we will say protons and neutrons each have a mass of 1, and electrons have a mass of 0. So, talking a little bit more about this average atomic mass of the elements, most elements consist of mixtures of all of the elements' naturally occurring isotopes. And it doesn't matter where we get those isotopes from. Or, I'm sorry, I'm just really messing this up today. Maybe it's my itchy nose. I'm trying to act like a rabbit, just in case you didn't catch on to that. I feel really weird explaining that now. I don't even know if I'm going to leave this in here. Yeah, I should. Okay. If I take a sample of an element from any place on Earth, the percentage of each isotope is going to be about the same. So when we look at the average atomic mass, we use the weighted average of the atomic masses of all of the isotopes. So I'm going to show you how to calculate that. It's pretty fun. Most students like it. Okay, so calculating the average atomic mass. It depends on both the mass and the relative abundances. So if I activate the pen, you will see that I am making sure that I have a color that I like. It keeps being red for some reason. I don't want it to be red. You can't see it very well. So a sample of copper has 2 isotopes, copper-63 and copper-65. Copper-63 has a specific mass in atomic mass units of 62.929559. That's kind of a number that's really brought out to many places past the decimal point. But this is what we know. 69.17% of copper is copper-63. 30.83% of copper is copper-65. And its mass is 64.927793. So to get an average atomic mass, we essentially have to take the percent times the mass plus the percent times the mass equals. But before we can do it, we have to convert the percent to a decimal. So since percent is per 100, we need to move the decimal place over twice. So 69.17 becomes 0.6917, and 30.83 becomes 30.3083. So here I'm going to set it up. I always like to write the percentage first, so I have 0.6917 times the atomic mass of this isotope, 62.9295999 plus parentheses 0.3083 times its atomic mass, 64.9277793 equals. Now when you punch these into the calculator, it's really important that you put parentheses here, because then you can just do it all in one swoop. You don't have to get a number here and then get a number here and then add them together. That's just silly and cumbersome. So if you type in parentheses 0.6917 times 62. End parentheses plus parentheses 0.3083 times 64. All of these numbers, end parentheses, equals, you will get 63.55 atomic mass units for the average atomic mass of copper. And this is what the periodic table says. Now most of the calculations we do will match. Sometimes there are mistakes and the number is really close. But what's most important to me is that you're setting the problems up properly. So let's look at another one. Silicon. I had students calculate this in class. We have 3 isotopes of silicon, 28, 29, and 30. And these are the masses. These are our percent abundances. So, same thing. Now I am going to strongly encourage you to, when you set this up, set it all up on one line if you can, because it's going to help really well with some upcoming problems. So let's move this decimal place over 2 places. 1, 2, that puts a 0 here. 1, 2, puts a 0 here. I write the percentages first. I have 0.9221 times 27.98 plus 0.0470 times 28.98 plus 0.0309. This is probably super boring as you're waiting for me to write these things. Times 29.97 equals, and if we plug in the numbers, we will, I think, get, I'm just going to look it up on the periodic table. I remember it. What element is this? Silicon. It will round to 28.09. I think students got 28.088. So 28.09. So there's another example. Now, here's a question. What if the isotope masses are not given? If this is the case, then we're always going to be given what isotope it is, and since this is a mass number, we just use that instead. So these are a little bit easier. So I'm just going to set up a table. We have magnesium 24, magnesium 25, and magnesium 26. Their relative abundances, 24 is 78.99%, 25 is 10.00%, and 26 is 11.01%. So even though you can see this right here, I'm going to write it out because I encourage that if you're watching this, you are writing these examples down so that you have them in your notes. Your notes would be a good resource for you to go back to if you are solving problems and need extra help. So percentages first. 0.7899 times, my mass number is 24. See on this bottom one here, I didn't start with the percent first, so I'm glad I'm doing this again because I like to start with the percent first. Not quite sure why I didn't do that. 10% becomes 0.1000 times its mass, 25, plus the next one, 0.1101. This pen is writing like a kindergartner again, times 26. Maybe if I write slower, it will work out. 24.32. Actually, that does work a little bit better. Atomic mass units. Da-ding, da-da-da-da. There, I got the answer. So these are a little bit easier. You don't have such big cumbersome numbers to use. And remember, we will only use them if masses are not given for these problems. Okay, the next scenario is how to solve for the unknown mass of a specific isotope when the average mass is given. So, look at the information we have. Here, the average atomic mass of chlorine is 35.45. Now, if you didn't know, if it wasn't given to you, you could look at any periodic table and get this information. I'm going to have to pause this for a moment. Peter just walked in. All right, I'm back. Sorry about that. So, I will start this again, and because I lost everything. So, the information given here is that the average atomic mass is 35.45 atomic mass units. This stinking pen color changed again. All right, so let's make a table with what we know. I know that I have chlorine 35 and chlorine 37. The abundance of chlorine 35 is 75.78%. The abundance of the other one is 24.22%. The isotopic mass of chlorine 35 is 34.968. Oh my goodness. 85271. This is not working out for me so well. And we are going to have our unknown be y. So we're going to set up the equation the same way, and this is why I wanted you to keep it all on one line, because it turns into a simple algebraic expression where we set it equal to this. So this is what we're solving for. So I'll set it up. I have my percent, 0.7578. Remember, I'm turning my percent into a decimal times this big number. It's kind of annoying sometimes when the numbers they give us are so big. Not necessarily big, but have a lot of digits past the decimal point. I'm sorry I'm writing this so slow, but I feel like it's the only way my pen works. I'm going to have to look into the settings with this. Alright, plus by percentage for the next isotope, 0.2422 times Y. What does it equal? It equals the average atomic mass. Boom. 35.45. Now what I want you to realize is that this is a simple algebraic expression, where maybe this is numbered, this is some number. Let's just say 18 plus 5y equals 59. Okay, so we solve it the same way. When we do the multiplication here, we're going to get a number. We subtract both numbers from each side. Minus 18. And that gives us that 5y equals 41. And then to solve for y, we divide each side by 5. 5's cancel. And I could go ahead and do the math to determine what y was. Now, if you're really confused about where I'm getting these numbers, it is just some numbers I pulled right out of thin air to show that this expression is not anything different than this. So we have a number plus a number times a variable, an unknown variable, equals a number. So that was the only purpose for showing that. Now, when the math gets calculated, it ends up looking like this. So here's that percentage times the mass plus the percentage times the unknown equals. And I just realized when I was writing on the previous slide, it says 35.45, but on this slide, it says 35.453. So I just caught a little bit of an error there. It's too late to fix. But what we end up finding is that y, not x. There's another mistake. I'm just rolling in the mistakes today. Rolling. Y equals 36.969 atomic mass units. So that is what the mass of a chlorine 37 would be. So that concludes my PowerPoint on atomic mass and finding average atomic mass, doing those calculations, and also determining the mass of a specific isotope if we're given the average atomic mass. Again, if this number isn't given to you, you can look on any periodic table and get it and use that resource. So thanks for watching. I hope that this will help you do your homework on, it's not really homework, we did it in class, but if you were gone, then I guess it will become homework for you. Or if you just need extra help because you were here and you didn't really understand, this will hopefully will have been helpful to you too. Alright, over and out. That's all I have for you tonight. Thanks for watching.